Hello everyone. In this video, we're going to be covering concepts from the course of Chemistry 1411, also known as General Chemistry 1. So as you can see, the topics that we're going to be covering today are the periodic table, components of matter, molecular weight, trends, and chemical formulas. The first thing we're talking about is the periodic table and how to actually get familiar with working with it. So the periodic table can be broken down into groups, which is going to be everything kind of up and down, so like a column. And our main group element on the periodic table is everything with an A. So group 1A, 2A, 3, 4, 5, 6, 7, and finally 8A. Our transition elements are going to be everything with a B. So 3, 4, 5, 6, 7, 8, and then it's kind of wacky over here because it's 1 and 2 to the far right. Those are going to be our transition elements. And remember, everything from top down is a group. We can also break it up into periods, so what we would consider a row. So a period, they're going to be numbered using these side numbers right here. So 1, 2, 3, 4, 5, 6, 7, and then it kind of shows that there's like a gap right here. These inner transition elements down at the bottom, they kind of fit in right here. But there is a purpose for them being farther down, and we'll see that in some of our videos. So the purpose of knowing these groups and these periods is because many professors, when you're first getting to know the periodic table, they will ask questions such as, tell me which element is in group 1A period 5. And so you would have to go to group 1A all the way down to period 5 and figure out what element that is. So it's pretty simple. Just know that your groups are going to be numbered at the top, your periods will be numbered on the side. The periodic table is also broken down into types of elements. So the two main groups are going to be our metals and our nonmetals. So our metals are going to have everything from alkali metals, alkaline earth metals. You won't really deal with these two right here. That's going to be the two that fit into that gap that we had talked about earlier. But we will cover transition metals, and then there's poor metals, and then we have our nonmetals, which is going to be pretty much nonmetals, and our noble gases. However, we can also break it up with one more group. So within our nonmetals, this group 17, or you'll see it as 7A, is going to be our halogens. So halogens is going to be your group 7A, your noble gases are your group 8A, and then we'll see it later on when we go through a more interactive periodic table. You'll see right here at this, I guess you can call it a staircase, you're going to have something called a metalloid. And we can actually talk about these in a later video on what exactly a metalloid is. So as you noticed, each element had its own box. And in that box, it has a bunch of information for the specific element. It's going to tell you the element's name. So for instance, we have carbon. It's going to tell you the symbol, so how we can identify when we're dealing with carbon. So carbon is going to be represented with the symbol C. It tells you its atomic number. So for carbon, it's 6, which means it's going to have 6 protons, and that's a very important information to know. And then finally, it's going to provide you with the atomic mass. So that's going to be the weight that the carbon atom weighs. And it's going to be the number of protons and neutrons that that atom has. And then before we move on to our next concept, I wanted to show you a helpful tool, and it's going to be ptable.com. ptable.com is an interactive periodic table website. And let me take you to it real quick so that you can kind of see all the tools that it kind of provides for you. So how we talked about earlier, if say you just want to look at metals, you can highlight the word metal, and it's only going to color the metal elements. If you switch over to non-metals, it only colors the non-metals, and then here are those metalloids that I was talking about earlier. And so if you actually click on these, it will give you kind of a definition of what they are, along with being able to just kind of identify what category things go into. If you highlight a specific box, you'll see the bigger box pop up right here, and it gives you all the information we had discussed about before. So it's atomic number, the symbol, the element, so hydrogen, and its mass or weight. We can also go to properties. So when you hit on the properties tab, you will see the different types of trends that the periodic table has. So let's click on electronegativity. So electronegativity is one of the trends you will have to know as a Chemistry 1 student. And so it kind of color coordinates to show you how electronegativity is increasing. So we see that we have really light colors on the lower left. We have really dark colors on the upper right. So as we are increasing from our lower left up towards our upper right, we can see that electronegativity is increasing because it's getting a darker color. You can also tell because it gives us numbers right here. So if I click on or hover over francium, we can see that the electronegativity is 0.7. But if I go up to fluorine, it has a 3.98 electronegativity. So it's a lot bigger. Along with any other trend that you might need, such as radius, density, pretty much anything you need, you can click on the property that you're wanting to compare, and you'd be able to see how it is related on the periodic table. They also have orbitals, which is another concept that you're going to be covering later on in the semester. So we'll talk about S, P, D, and F orbitals, and you'll have to be able to fill in the structures. So it's a very helpful tool to use this whenever you're getting used to it and you're doing your homework. So say you assume that you have helium and you want to say that it's a 1s orbital with 2 electrons. So you can hover over it, and then you see that yes, it is a 1s orbital with 2 electrons in it. So it kind of shows you what your configurations will look like. You can also go to look at isotopes and compounds. So it is a very helpful tool, and I do hope that you utilize this tool. So now we're going to move on to components of matter. Altogether, we're going to cover 4 components. The first 2 are elements and molecules. An element is the simplest type of substance with unique physical and chemical properties. An element consists of only one type of atom. It cannot be broken down into any simpler substance by chemical or physical means. So this means you can only have one type of atom. So such as like hydrogen, you can only have hydrogen, or you can only have oxygen, carbon. You can only have one type for it to be considered an element. And for those that didn't know, a substance is matter whose composition is fixed. And then finally, we have molecules, which is a structure that consists of 2 or more atoms that are chemically bound together and thus behaves as an independent unit. So in nature, we have, say, oxygen, but you'll never see oxygen by itself. you're always going to see it as O2. So O2, it's two atoms, however, it's the exact same element. So that will make it a molecule. So O2 would be an example of a molecule. And here is a visual representation of what and how to kind of recognize them when you're looking. So an element is going to be one atom. So let's say all of these are just little hydrogens or carbons. And then we see our molecules, which is two or more, depending on what you're looking at, of the element. So we have, like, say, two oxygen or two hydrogen. And those will be our molecules. We then have compounds and mixtures. A compound is a substance composed of two or more elements that are chemically combined. So this time we're going to have two or more elements. So it wouldn't just be H2, it would be such as H2O, so water. A mixture is a group of two or more elements and or compounds that are physically intermingled. So let's look at a visual representation of what these actually mean. So a compound is going to be two or more elements. So I have, in this particular example, I have one central element, and then I have three other side elements right here. So because they're the same color, we can assume that we have three of one element and one of the other that are coming together to form a compound. For a mixture, we see right here, we have elements, we have molecules, and we have compounds, all together just kind of intermingling with each other. Within a mixture, there are two types. We have a heterogeneous and a homogeneous. A heterogeneous mixture has one or more visible boundaries between the components. So this could be such as mixing water and oil. So if you've ever tried mixing the two, you notice that they never actually mix together. There's always a visible boundary in between them. So that would be considered a heterogeneous mixture. A homogeneous mixture has no visible boundaries because the components are mixed as individual atoms, ions, and or molecules. So an example of a homogeneous mixture could be salt water. So when you put salt in the water, stir it up, you don't actually see the salt floating around in there unless you have a very concentrated amount. But normally you'll just see what you think is water because it has no visible boundary separating the salt and the water from each other. A homogeneous mixture is also called a solution. So we would have a saltwater solution if we mix salt and water together. Solutions in which water is a solvent, so a solvent is something that will dissolve what you're putting in, are aqueous solutions. So because we said we were mixing salt and water together, and the water is kind of dissolving the salt, it would be considered an aqueous solution. The properties of an element. All elements are made up of the three subatomic particles, and they're going to be protons, which will have a +1 charge, neutrons, which are neutral, they're not going to have a charge at all, and electrons, which are going to have a -1 charge. So, for instance, if I had H+, that little plus kind of shows you that +1 charge. And then also the location is very important. So protons and neutrons are going to be located in the nucleus. This is why it makes up the weight of the element that we're looking at. And then our electrons are going to be located on the outside of our nucleus. atomic symbol, number, and mass. So in some instances, you're going to see your element represented in this format. So it's not always going to be shown the way that you see it on the periodic table. So X is going to represent where your symbol would go. So if you had a carbon, you would have a C. If you had hydrogen, you'd have an H there. It's just going to represent what element you're dealing with. Your A is going to represent your mass. So remember, on the normal periodic table, it shows at the bottom. But for this representation, it's going to show you at the top left-hand side. So your mass is going to have your protons and your neutrons added together. And then Z is going to represent your atomic number. So that number that was on top of your element is now going to be right here in your lower left-hand side. And that's going to be the number of protons. It's very important to know this because using your atomic number and your mass number, you can determine how many protons and how many neutrons your element has. So let's do a practice question. How many neutrons does magnesium have? So let's go over to our boogie board and work it out. So we have Mg with a 24 on top and a 12 on bottom. So if we write out our general setup, so we had X, which is going to be represented with our Mg, we have A, and we have Z. A is going to be our mass, and Z is going to be our atomic number. So now you have to remember which one is protons, which one is protons and neutrons. Remember, the mass is going to be what makes up all of its weight, and it's what's inside our nucleus. So this, our mass, is going to be our protons plus our neutrons, while our atomic number is simply our protons. And we want to know how many neutrons we have. So what we can do is we can take our mass and subtract our atomic number, and we'll be left with our protons. Because if you take the mass, which is protons and neutrons, and subtract the number of protons, you now have just neutrons. So our mass is going to be 24. We're subtracting our protons, which is 12. So we'll be left with 12 neutrons left. And that's all you have to do for this problem. Now we're going to cover the concept of molecular weight. Molecular weight is a number equal to the sum of the atomic masses of each atom in the molecule or compound. So, if I want to know the molecular weight of CH4, I know that each carbon is going to weigh 12.01. I only have one, so I say 12.01 plus the weight of our hydrogens. Hydrogen is going to be 1.01 times 4, because we have 4 of them. When you add those two together, you'll get a total weight of 16.05 grams per mole. So let's do one on our own. What is the molecular weight of glucose? Glucose being C6H12O6. So let's go over to our boogie board and work the example. So we have C6H12O6. And we now need to figure out what the weight is for each of our individual elements. And you can determine that if you go to your P table. So hydrogen is going to be 1.008. Carbon is 12.011. And oxygen is 15.999. So we now have the weight of each individual element. And now we have to take into account how many we have. So we have 6 carbons, so we take the weight times 6. We have 12 hydrogen, and we have 6 oxygen. And when we do the math, the total weight of carbon is going to be 72.066. The weight of hydrogen is going to be 12.096. And the weight of oxygen is going to be 95.994. Now we want the weight of the entire compound, so we're going to add all of these together. So altogether, we get a weight of 180.156 grams per mole. And this is going to be the weight of our glucose. Go ahead and pull our PowerPoint back up. So we now know that the molecular weight of glucose is going to be 180.156 grams per mole. And now we're going to talk about periodic trends. So there's 4 trends that you're going to have to know for the General Chemistry 1 course. The first is going to be ionization energy. So ionization energy is going to increase as we move right and as we move up. So going towards that fluorine that we saw right here, our ionization energy will increase towards the upper right-hand corner, which means it will decrease towards the lower left-hand corner. The second is electron affinity. Electron affinity and ionization energy will have the exact same trend. So as we move up towards this upper right-hand corner, our electron affinity will increase, and as we move down towards the lower left-hand corner, our electron affinity will decrease. We then move to atomic size, which has the exact opposite trend. So as we move towards our lower left-hand corner, our atomic size, or radius, will increase. So that means that the size of the element is going to be bigger as we go towards our lower left-hand side. When we move to our upper right-hand side, that means we have smaller elements, or smaller size or radius. And then finally, metallic characteristics. So as we are moving in the same direction as our atomic radius or our atomic size, our metallic characteristic is going to increase. And then as we move to our upper right-hand side, the non-metallic character will increase. So we become more metallic, we become less metallic. We increase in size, decrease in size, increase in electron affinity and ionization energy, and then decrease in ionization energy and electron affinity. So really all you have to know is this table to be able to answer the types of questions you would have on your exams. So let's go through a couple possible questions that you could see. List the following in increasing atomic size. And so you're given Mg, Fr, Rb, and Al. So let's go to our boogie board to work these through. So they said to order them in increasing size. So size had the trend that it was increasing to the left and increasing down. We were given the elements of Mg, Fr, Rb, and Al. And we need to put them in increasing size, which means that, let's see, we have 1, 2, 3, 4, so 1, 2, 3, 4. As we list them, our biggest is going to be over here, and our smallest will be over here. So what we can do is go to the periodic table. and we just find the elements that we're dealing with. So we want to find the, let's say, the biggest. So our FR is right here, that's one of them. RB is right here, so we know that FR is bigger than RB because it's farther down. And then we have MG, which is up here, so we know that that's even smaller than RB. And then we finally have AL, which is over here. So what it appears is that AL is our smallest, and as we move over, we hit MG, which is our second smallest. And then we go down, we hit RB, which is our second biggest. And then finally we hit FR, which is going to be our biggest. So we get this order right here. Go ahead and go back to our PowerPoint. And we'll have another example. So this one says, which of the following has the lowest electron affinity? And they gave us F, TE, CS, or CR. So we just want one. We don't want to order them. We just want to know which one has the lowest electron affinity. So if we think about it, electron affinity is going to increase in this pattern. So this was electron affinity. So this is the direction that it increases. So we want the thing that is going to be closest in this direction because we want the lowest. And we have F, TE, CS, and CR. So what we have to do is go back to our periodic table and see which one is farthest to the lower left-hand side. So our F is way up here, so there's a likelihood that that probably isn't our answer. We have to find our TE. TE is here, so automatically we know we can cross F out because it's farther, TE is farther down. So as of right now, out of the two, that is our lowest. We now need to compare it to CS. CS is way down here, so that's even farther down. So we know TE can get canceled out. And then we have CR. CR is right here. Because our CS is farther down, our CR gets canceled out, and we're left with CS as our lowest electron affinity. Go back to our PowerPoint and talk about chemical formulas. There are three different chemical formulas that you'll have to get used to writing out. There's the empirical formula, the formula for a compound with the smallest whole number mole ratio of elements. This will make a little bit more sense when we start doing some practice. There's the molecular formula, the formula for a compound with the actual number of atoms of each element in a molecule. So if we have 3 hydrogens, then you would have H3. You would have every single atom of the element actually written out. And then there's the structural formula, which is the formula that shows the arrangement of atoms in the molecule of a compound. So here is a visual understanding. So the empirical formula will sometimes be the same as the molecular formula if you're unable to condense it. So let's look at our first example. So we have our molecular formula, which is going to show every single element we have. So we have 2 nitrogens and we have 4 oxygens. The empirical formula is going to be that condensed version. So because we have 2 and we have 4, both can be factored by 2. So 2 goes into 2 one time, 2 goes into 4 2 times, so you end up with an empirical formula of NO2. And then the structure formula just kind of shows you what the structure is going to look like. And then finally, we have water. So we have H2O as our molecular formula. The smallest would be a 1 here. 1 goes into 1 1 time, 1 goes into 2 2 times. So we realize that our molecular and our empirical formula will be the same for this instance. And then our structural formula of what it will actually look like. So I'm going to show you a brief video on making empirical formulas from the molecular formula.
In this video, we're going to learn how to write empirical formulas, just this, for all of these molecular formulas. Here's our first example, C8H18, which represents a compound that has 8 carbons and 18 hydrogens. To write the empirical formula, we do kind of the same thing that we do when we have a fraction, and we want to get it into its simplest or most reduced form. We look at both of these numbers, 8 and 18, and we ask, what is the biggest number that we can divide both of these by to get them as reduced as possible? Okay, so in this case, we can divide both 8 and 18 by 2. They're both divisible by 2. And dividing both of these by 2 is exactly what we'll do to get the empirical formula. It will look like this. We'll have C, and then 8 divided by 2 is going to give us 4. And we have H, 18 divided by 2 gives us 9. Okay, so now we got 4 and we got 9. Check it out. We can't divide both of these by the same number anymore, okay? That's how we know that this is in its simplest or most reduced form, and it's how we know that we now have the empirical formula, okay? Let's look at a couple more. C8H6O4. As before, we want to ask what's the biggest number that we can divide all of these by to get this as reduced as possible, okay? We can divide all of these numbers here by 2, just as we did up here. And so the empirical formula is going to look like C, 8 divided by 2, 4, H, 6 divided by 2, 3, and O, 4 divided by 2 is 2. Okay, how about with this one? C3 and 12. What can we divide everything by here to reduce it down? Okay, both 3 and 12 are divisible by 3. So we'll divide these by 3, and we'll get C. 3 divided by 3 is 1. But remember, when we're writing chemical formulas and we have a 1, we just don't write anything. So it's just going to be C, and then it's going to be N. 12 divided by 3 is going to give us 4. So this is the empirical formula. Okay, P2S3. What can we divide both of these numbers by to get this as reduced as possible? Nothing. There is nothing that we can divide both of these numbers by, right? They're not divisible by the same numbers. So because of that, P2S3 is as reduced as it can get. So that means that the empirical formula in this case is exactly the same as this molecular formula. And sometimes that happens. Often you'll have molecular formulas that can't be reduced down anymore, and their empirical formulas are exactly the same. So don't freak out if you get a formula like this you just can't reduce. It's fine. The empirical formula is just the same as a molecular formula. Okay? How about H2O2? Well, in this case, we can divide both of these by 2. So our empirical formula will look like H, 2 divided by 2, which gives us 1. We don't write anything after it if we have a 1, so it's just going to be H. And then we have O, 2 divided by 2, which also gives us 1. We don't write anything after it, so just HO is going to be the empirical formula for H2O2. Okay, now, if you feel you've really gotten the hang of this, you still might want to watch me do a couple more because I'm going to talk about a few examples that sometimes trip people up. It can be a little bit tricky. S8. In this formula, we just have one type of element, sulfur, but we still go through the same process to write the empirical formula, okay? Can we divide this number by something that will reduce it even more? Yeah, 8 is divisible by 8. So our empirical formula is just going to be S, 8 divided by 8, which is 1. So the empirical formula for S8 is just going to be S, okay? How about C6H6, okay? In this case, both of these are divisible by 6. So the empirical formula will be C, 6 divided by 6, 1, so we put nothing after it, and then H, 6 divided by 6, which is also 1. So we don't put anything after that. So it's just going to be CH is the empirical formula for this. Now, one thing that I just want to point out here is that oftentimes many compounds can have the same empirical formula. All right, C6H6 has this empirical formula, but all of these other molecular formulas, as well as many others, have the same empirical formula right here. The empirical formula for all of these is CH. So oftentimes you'll see a bunch of molecular formulas that have the same empirical formula. So just keep that in mind. Okay, 2 more. C12, H10O, and there's nothing after it, so it's O1, okay? What can we divide all of these by to simplify it more? There is nothing. Just as we saw before, when you can't further simplify a molecular formula, the empirical formula is just the exact same as a molecular one. So that's all we do, okay? Here's the last one. B3N3H6. What can we divide everything by? We can divide everything by 3. So we're going to get B, 3 divided by 3 is 1. We don't put anything. N, 3 divided by 3 is 1, so we don't put anything. And H, 6 divided by 3 is 2. So that's how we can take molecular formulas and write empirical formulas for them.
All right, so hopefully that video helped you get a better understanding of how to actually go through the process. So let's go ahead and work an example of our own. So we have C6H12O6, and they want us to determine what the empirical formula is. So let's go to our boogie board and work that out. So we have C6H12O6. So we have to figure out what can go into 6, 12, and 6 to make it in its simplest form. What we get, both are divisible by 6. Oops, sorry. Got ahead again. So we write C, 6 divided by 6 is 1, so we don't have to put anything. H, 12 divided by 6 is going to be 2. And then we have O, 6 divided by 6 is 1, so C, H2O is going to be our empirical formula. Not too bad after you see a couple examples. The empirical formula of a compound is CH3. So now they've given us our empirical formula. Its molecular weight is 30 AMU, or 30 grams per mole. What is its molecular formula? So this time we're working in the exact opposite direction. So let's go to our boogie board and figure out how we would solve an example like this. So we know its empirical, or its simplest form, is CH3. We know that the weight of our molecular formula is 30 grams per mole. So what is the extended form of our CH3 with a weight of 30 grams per mole? So what we can do is figure out what is the weight of our empirical formula. So if we go to our periodic table, we can get our weight. So carbon is, carbon equals 12.011. Hydrogen is 1.008. So let's go back here. So these are the weights of them individually. We have 3 hydrogen. So let's just round to the wholest, the nearest whole number. So we have 1 12, so 12 plus 3 times 1, so 3. So that gives us a weight of 15 grams per mole. So our empirical formula weighs 15. So what we can do is we take the weight of our molecular formula, which is 30 grams per mole, so 30, and we divide by the weight of our empirical formula, which is 15, we're going to get 2. So this means that we're going to take 2 times our empirical formula. So 2 times CH3, which means we will multiply the 2 into both, and we'll end up getting C2, because we had a 1 here, so 2 times 1 gives us 2, so C2. 3 times 2 gives us 6, so we have H6. So our molecular formula is going to be C2H6. And what you can do, you can always add up the weights to make sure that it is going to work out properly. So if I just take the whole number, so 12 times 2, we'll get 24, H, which is 1 times 6, so we say 6. So 6, 7, 8, 9, 10, put a 1 here, 30. So we have 30 grams per mole, which means yes, C2H6 is our molecular formula. It is very important that you try to go back and do this step right here just to verify, okay, with these numbers plugged in, this does make sense for the information I was given. So let's go back to our PowerPoint. And that wraps up pretty much all the concepts that we're covering today. So let's do a brief overview of everything that we covered. So the first thing that we covered is the periodic table. We discussed the difference between a period and a group. So remember, your groups will go up and down, while your periods go left to right. We also broke them down into categories, such as halogens, noble gases. We discussed metals and nonmetals. So really get familiar with how your periodic table is set up. We talked about the components of matter, such as elements, molecules, compounds, and mixtures. An element will be by itself, so just hydrogen. A molecule will be two compounds together, sorry, not compounds, two elements together, such as H2 or O2. A compound will be two or more different elements, such as H2O. And then we talked about mixtures, such as hetero and homogeneous mixtures. We talked about solutions and what it takes to be an aqueous solution, so water. We discussed molecular weight, which is the sum of all the weight, the weight of all the atoms in a compound. So we take the carbon, the weight of carbon plus the weight of hydrogen, we can add them together and get the weight of CH. We talked about the trends, so ionization energy, electron affinity, atomic size, and metallic characteristic. So it's very important that you know how they increase and decrease on the periodic table, because you will have to know those trends for your exams. And then finally, the last thing that we covered was chemical formulas, where we talked about the empirical, which is our simplest form, the molecular, which is going to show every single molecule that you have, and the structural, which is going to show you the structure that the compound has. And that covers everything that we have. So I hope that this video was helpful, and best of luck on your examples.